Very good morning to all of you. So we have with us today Dr. Devanand, who will be presenting on the topic of AI applications in energy storage systems. So Dr. Devanand has worked as is working as senior engineer in the education team at MathWorks India Private Limited, Bangalore. His expertise lies in model-based engineering workflows for electrification applications. Dr. Singhdeo has an interdisciplinary background, having bachelor's in physics honors, followed by MSc PhD degree from the Department of Energy Science and Engineering, IIT Bombay. In previous roles, he has also worked as a postdoctoral fellow in Department of Energy Technology, Aalborg University, Denmark, and faculty at day5 University, Assam, India. Sir, I welcome you, and may I kindly invite Dr. Prem Kumar sir to hand over the ceremony as a welcome gesture.
So I guess this is the final day of the whole FTP. So we'll try to keep things not very heavy. So whatever content I have, initially I will take you through some of our workflows in the area of, as I said, AI applications in energy storage systems. But all these examples that I'm going to use, they are available. So if you have a laptop, you can actually use a laptop to have a hands-on experience with examples. So basically what we will cover today, the agenda will be in this particular area. So applications of AI, we will have some focused applications looking at this couple of different areas. One is a simple use case story of how you can use AI specifically to sort through a big database and identify suitable materials for a particular application, which is what some users have done. but we will focus mainly in the area of battery management systems, where AI-related solutions are sort of now making their way, specifically for certain estimation processes, okay, like state of charge, state of remaining useful life. So we will look at examples that cover particularly these focus areas. Apart from that, if you have anything on your mind that you would like to explore, that should also be totally fine with you. So broadly, when it comes to energy storage, it's in the broader context, there are so many different things that come into the picture. Right? So energy storage could be in the form of electrochemical, so what we are going to focus on. But nowadays, for electrical applications, people also look at flywheels, sort of, which add some sort of an inertia to, let's say, an integrated energy system. Thermal systems, we can store some amount of energy in a thermal system, and then pumped hydro. So pumped hydro is also very interesting. I was in Denmark, so I know a user story that on particular days in Denmark, they used to generate so much energy that they could have powered the whole country for a year. So what do? They store that energy in pumped hydro. So they sell that electricity to Norway. Norway had pumped hydro, so they would just pump that water in their region. And then later, when other parts of Europe had shortage, they would sell that electricity back from pumped hydro. But today, as of now, we will just focus on the normal batteries, like electrochemical batteries are what we are going to focus on. So everyone is familiar here with how you actually model batteries, or do you have any course here where you actually model batteries? Any course where you model batteries?
Battery management system.
So battery management course, it is there. So everyone is familiar with batteries, how you model and how you actually design battery management systems. Okay, so if you have any questions particularly, any other detailed question also, we can take it up as we go. One more bigger landscape, but we are talking about storage. It is part of a much bigger landscape. If you see here, you can spot that overall the whole energy landscape we have divided into three main areas. One is the generation aspect of it, where we can generate energy from different sort of sources, solar, wind, it could be hydro, multiple of them. We have clubbed all of those together. So when it comes to using MATLAB and Simulink there, we can model all of these different sort of systems, both the plant level and the controller level, and then we can do the hardware aspect. Similarly, we have the storage systems. So people, what they do, they model these sort of systems in detail. Once they model the systems, you look at the control aspect of things or the management aspect of things. And then the conversion distribution aspect, where whatever energy we are generating, we are using it at a different location. Okay. So overall, when it comes to these areas, we have a couple of points that we sort of look at. So MATLAB and Simulink is used not just to model the systems, but designing the controls and then looking at performance analysis. So in performance analysis, there are a lot of different things we can do: stability analysis, techno-economic analysis, different sort of statistical studies. So just to give you a broad picture, a lot of different areas can be actually coming under the performance analysis also. And last thing is forecasting and monitoring. Often, when it comes to any sort of energy usage scenario, people always plan for it. So we try to predict what will be the energy usage at a given point in time. That is also where we can actually use MATLAB and Simulink, and probably AI is also going to come into the picture. So looking into the whole aspect, can you identify some of the areas where AI can play an important role? Control. Control, definitely. So people are working with advanced controllers. So reinforcement learning is a very important area where people are using AI methods. If you have data, you can train very advanced sort of control algorithms. So that is great. Any other area? Forecasting. So forecasting I mentioned, it's a very important area. Definitely you can, if you have some data available, there are different ways you can actually forecast the energy required at a particular point in time. What about performance analysis? So definitely there are a lot of statistical tools which are there, but not just that, fault studies also if you do, if you have some historical data available, often with some parameters we should be able to predict where the fault is going to happen. So today we will look at some examples from some of these areas related to storage. So MathWorks, I think most of you are familiar now with the tool. So broadly, we have MATLAB, which is the base platform for modeling and simulation, where you can create algorithms, you can create different sort of applications, and on top of that we have Simulink. So Simulink is the environment where you can actually do model-based design. So this is widely used in the industry. So directly whenever you prototype an algorithm, you can take that algorithm to different sort of prototyping environments. You can have hardware, you can have business systems. So that is what you can do from Simulink. Plus, there are all these different toolboxes which are there, which allow you to do certain specialized tasks for different domains. So, from electrical perspective, any particular toolbox that you are familiar or have used before?
Yes, subscribes and power system and the process control process, DSP tool process.
So, that's very interesting. I think process control DSP, that's something new. So apart from that, anything that you have tried? Motor control and you have tried?
Control, yes.
So primarily you are familiar with the toolboxes also. So today some of the toolboxes that we are going to use will be from the AI aspects also. So are you familiar with the AI toolboxes which are there?
Yes.
So there is primarily two. Okay, there is a statistics and machine learning one, which allows you to create statistical model, machine learning models, so that we can train. And then there is a deep learning one also, which is there. Okay. What we are not covering here today is the reinforcement toolbox, which is there. Okay. So additionally, there are more toolboxes which could also be sort of be applicable. So we'll mostly look at a couple of toolboxes from the AI today. So I think this I already covered. So this is a base MATLAB. And just to give you a reference, so researchers have started using this. So statistics and machine learning toolbox, the good part is that you can bring in any data set that you have. Then in the particular environment, we have a lot of models which are already there. So you can explore how this sort of models would work. So this is something that a researcher group actually did. So at Stanford, they were identifying different sort of battery materials. So how do you identify a proper candidate for a particular battery application? So ideally, what they were looking at is their atomistic structures. So from their atomistic structures, it is possible that there could be a lot of different candidates. So they took the atomic structure and based on that, they started training different models. So they looked at least square regression, then SVMs, and then try to identify what would be the right battery for that particular application they were looking at, and they got a plot like this. So you can see the promising candidates lie at the right hand type of here, where you have the model extrapolation, and so based on superionic likelihood, they were able to classify what could be the right candidates that they can use. So those who are working from a material application, they can try something like this to identify a particular battery material very fast. Otherwise, if you go the lab route, it would actually take a lot more time. So they were saying that for a different scientist, he might take 3 to 5 times more time to actually come up with a material like this. So key industries which may use MATLAB and Simulink. So the major, if you look at the industry use, automotive and aerospace industries are the major users of MATLAB and Simulink. Are you aware why is that?
We capture the dynamics of the system, real dynamics.
That is good. So dynamics you can capture, but you can do it in base MATLAB also. Right? You can write the code in MATLAB and capture some dynamics. So they use something called model-based design for this sort of applications. Any idea why they do that?
Powertrain.
Powertrain they can model, that is true. But why do you use model-based design?
To understand the system
Okay, so
instead of testing real one models.
that is true. Sir has pointed the right thing. So let's say today I want to build an automotive system.
Okay.
How do I know it is performing rightly? I have to take it to the real world and then test it. So when you take it to the real world and test it, you will generate a lot of data. So previously, in the automotive industries in Germany and all where they were working, they had test tracks. So they would build an automotive, drive it onto the test track, come back with the data and then try to see how they can improve. So it was a very long process, very costly because you have to build multiple prototypes. Instead of that, in the modern day world, what is happening is that you are building the whole vehicle as a model. You are building control systems for the whole vehicle. Okay, and then you have certain requirements that you want to match. Certain requirements in terms of performance, certain requirements in terms of range. So once you build a vehicle with the control systems, instead of building a physical prototype, what you do is that either you create a virtual environment where that vehicle moves about and you see how it performs, or you bring in certain hardware. So there are hardware which you can bring, real-time hardware, you can generate code for that hardware. Okay, and you can generate code for the controller, then do the testing and see whether the vehicle is performing properly, and then go back and iterate. So you don't have to build a physical prototype. Everything is being done by using models. There is one more advantage of it. You can relate to it if you think about aerospace, defense. A major advantage is that you have to ensure that these systems are safe. So you have to do a lot of verification and testing. That is why MATLAB and Simulink, what it allows you to do, it allows you to create a lot of tests based on the requirement that you have. So once you do this sort of tests, then you can confidently say that it will perform as you have designed. So that is why they actually majorly use MATLAB and Simulink in these particular industries, because it's safety critical. Plus, things are happening, progressing very fast. So nowadays, if you look at automobiles, people are thinking of and comparing it with mobile phones. Do you know why? Because if you look at each of your mobiles, it might be from the same company, but it's very personalized. You have your own apps. So they are looking at how you can personalize a vehicle sort of a thing. How can you do that? You can only do that when you are able to provide different sort of features for customized for a particular user. So these sort of models are going to come. Okay. So how do you customize? You have to be ready with some models and you can directly generate code and application for that particular vehicle. So the industry is moving towards software dependent vehicles, okay, SDV and all platforms. Apart from that, energy is also very important area. Also same sort of reasons also add here. They use model based design here. The design is there. You can actually test a system before you deploy it. Okay. Like if you are working in the renewable energy domain, if you have model an entire system like a microgrid and controls for that microgrid, before you test it with a real system, you have to show it to the people that it actually works as you have designed. So there are different protocols and different aspects and standards it has to meet. So those are aspects that you can get done when you use MATLAB and Simulink. So these are some of the companies I have listed who actually use MATLAB and Simulink, and if students are familiar with the workflow, these are some of the industries where they can actually target. So you can see a lot of automotive companies here, lot of aerospace companies here, but you will see different industries also, energy industries, industries from pharma, service-based industries. So widespread, a number of industries actually use MATLAB and Simulink. So Simulink we covered. So Simulink is the base platform. I think all of you are now familiar with Simulink. Okay, so you have blocks. So with blocks you actually build models. Just by connecting blocks, you can actually build an entire algorithm. And the benefit that you get here is that, what is the benefit that you get compared to MATLAB when you do it in Simulink?
graphical user. This is graphical user interface, so
Yeah.
don't need too much code.
So you don't need coding, so it's quite easy to understand. Plus here you can design a larger complex system. So a system typically has a number of components, and these components are connected together, coupled together very closely. So that is something we can build here very easily. So I will not then go much into details of Simulink here. So I have taken one example, maybe we will see a lot more in detail later. So companies like Evlo. So I think this is one emerging area. A lot of companies are now working on large scale battery energy storage systems. Have you heard battery energy storage systems? A lot of companies, if you look like Evlo, I have given this is one name, but Siemens and all, they have solutions when it comes to battery energy storage systems. So here if you see, they have 4 megawatt hour energy storage system coupled with a PV solar farm near Montreal, Canada. So they have taken a big battery energy storage system and combined it with PV. So why would I do that? Something like that. Why you need a battery system when you already have a PV system which is generating power? And batteries are very costly, by the way.
To store the surplus power.
So PV and all, yeah, so you actually store surplus power. But why need something so big like 4 megawatt hour energy storage system? Why huge in terms of energy storage capacity? So recently, not very long, I was in a conference in Bangalore only. So we had a lot of people who came from Europe. They were presenting a very interesting use case from Spain this year. Have you heard? Spain had a massive blackout. Have you heard so what actually happened in Spain? Spain has big solar farms. Big solar farms are there, and they generate a lot of electricity. If you look at their neighbors, France and all, which are nearby, but what I heard is that Spain in itself, they did not have a lot of storage available for them for electricity, storing electricity. So when they had a grid fault, it sort of, because they did not have any sort of an inertia, it just escalated very fast, and none of the countries nearby were able to also support them with additional power. So their grid totally collapsed. So in the coming time, given that we are looking at a lot of renewable energy mixed into the grid, this sort of battery energy systems are going to play a very important role. And it is not just the technological aspect, but one very key thing is also to understand and size. What is the size of battery energy storage system that you will need at a place? Because cost of the systems are also very high. So what they do, typically if you see, what they want to do is that they want to extend the lifespan of this sort of battery energy storage systems, because it's very costly. How do they do that? They actually use model-based design to model the controllers. So they do a lot of simulation-based tests, and they generate code for different sort of targets. So that is the advantage that MATLAB and Simulink allows you to do. You can model an entire big solar farm, you can couple a battery energy storage system, and then you can see how you can improve the lifetime of these sort of systems. Okay, so they were able to do it very fast. So that is the advantage that model-based system allow you to have. So now we will go into the AI related applications. So AI also everyone probably might be familiar with, right? So AI is a big mega trend. If you look at year-wise, it actually got up very fast in the year 2015. So broadly, AI is divided into a number of categories. So one important area is machine learning. So I think given that this is the last day of the FDP, you might be familiar with machine learning and deep learning, right? Okay. So I'm not going into the detail of that. So, but in machine learning, basically you have data, you get the algorithm. It is of two types, supervised and unsupervised. In supervised, we give it hint at what that data is, and in unsupervised, the data is not even labeled. It itself tries to find out certain pattern. So there are 2-3 types of this machine learning, and then there is deep learning where you have neural networks where we do not need to actually explicitly give any characteristics. It will automatically take the data, find the features, and give me the trained model. So the example that I am going to talk about now, this is very important nowadays, that AI is not something that is in silo. It is often part of an integrated system. AI separately you don't get. AI is often part of a larger system. So here I have taken an example of a battery management system. So if you look at the left hand side, we have the plant, which is basically the model of the battery. Okay. Then we have the battery management system. So battery management system actually controls the output of the battery, and it also ensures the battery has a longer lifetime and it doesn't end up into any hazardous condition. So here, this is how the typical load is going to look. So battery plant consists of how many parts? 2-3 parts will be there. One is mainly the battery model. It could be a single cell or it could be a number of cells connected together to form the battery pack. It will deliver power. So it has, if you look here, it has a particular power electronics attached to it, which ensures that it delivers the right amount of power for an application. Plus it will also be getting charged and discharged. So for the charging cycle, we have the model of the charger also, which is there. Then we have the battery management system, where we have all the supervisory logic that is needed to ensure that the battery performs its functions in a very proper way. So one key thing that we are going to look here when it comes to integrating AI is specifically the SOC estimation. So normally SOC means state of charge of a battery. So whenever we have a particular battery, we are storing some amount of charge in it, and we quantify the amount of charge being stored with the parameter known as state of charge of a battery. Now the question is, we cannot actually directly measure the state of charge of a battery. Why is that? Why cannot we directly measure the state of charge of a battery?
Because each battery is each cell is having a different level of charge.
That might happen during charging and discharging. Different cells might have different charges. But can't I have a parameter for, let's say, this cell? SOC is, let's say, 20%. For this, it would be 40%. I can't do that. So what is the challenge here?
Sensors. Current we can measure easily and the charge.
That is true. So we cannot actually measure the charge inside. How are you going to see how much charge is being stored inside? Sensors? You can't put any sensors inside. So I give an analogy. So if I'm filling a bucket with water, I can actually see and pour a particular amount of water, and then you see something like this. Okay. And looking at this, we are directly intuitively saying that we have this much charge. But this is something that you cannot see inside a battery. This is something you cannot see. So we have to indirectly come up with the state of charge of a battery. So typically, if we think from the sensor perspective, we can sense two things. We can sense current and we can sense voltage. So from current and voltage, we should be able to say what is the state of charge in the battery. Okay. So you got my point. You cannot see inside the charge. The only thing you can do, you can sense the current and the voltage. Okay. So Madam mentioned that we can measure the current. So what if I do something like this? I just integrate. I measure the amount of current I am taking from the battery, measure the amount of current I am putting inside the battery. Will I get a proper state of charge? Can that be a proper way of defining the state of charge? I'm measuring. Okay. So just to understand how the problem is, we are just trying to understand what is happening. We are measuring how much current I'm drawing from the battery and how much I'm storing. Just based on that, can I come up with a consistent value for state of charge? They do that actually. So that method is known as Coulomb counting. You count how much electricity is going inside the particular battery. You count how much is coming out. From that state of charge, if you have, do you think that is going to be accurate? How many of you think that is going to be accurate?
It's a continuous thing, like you cannot say that start from here, this instant T1, set T2. If you have fixed everything, within that period you can. Otherwise, it is always approximate. Yes.
Correct, your conditions might be different. So you cannot exactly say from that also. You do that at a different temperature, you do that at a different condition, you will get a different sort of a value. So often when you have state of charge based on Coulomb counting, what has been observed that over a period of time, there is some divergence. You won't be able to have a consistent, accurate value. So it's not a very accurate way of doing that. So what we are trying to do is we are coming up with something like a virtual sensor. So this term has now become very interesting in the industry. People are calling it like a virtual sensor. What it does is that it mimics a real sensor. So maybe if you could put a real sensor inside the battery, it should be able to give you the state of charge. Instead of that, we are virtually trying to estimate that. So the sensor is not in a real sense, it's a virtual sensor that we are implementing. So physical sensor, and this is not just valid for battery, I put it for battery, but this is a term that is broadly applicable anywhere where you cannot put a physical sensor, instead you are going up with virtual sensor. So it could be expensive, it could be slow, noisy, unreliable. So if these quantities are something that you see, then you can actually go with a virtual sensor. I have one more very interesting use case that I heard where a virtual sensor was used. So Mathos team was only working with Indian Railways where they were trying to measure the vibration of the coaches which are there. They had to actually use a virtual sensor. They could have put a real sensor, but they could not. Okay, so they actually had to put a virtual sensor. Interestingly, what Railway said that they actually tried with real sensors, but it was getting stolen. So it could be those sort of scenarios also. Right? So virtual sensor is something where you cannot go with a real sensor. So with batteries nowadays, people are using different sort of virtual sensors. How can we build something like this is something that we will take a look at. So directly, as I mentioned, you can go with first principles based model. So state of charge using Coulomb counting, the one that we were discussing before. Because you know the equations, you can see the equations. It will be falling in the first principles aspect. Then there are data-driven models also, which are something that we will take a look at later, which is where AI comes into the picture. Is that all? No. So what people are also doing is that they are combining first principles and data-driven and coming up with intermediate models. So that is the last way also one can go about. So you can have intermediate combining both of them. So Coulomb counting, it's not very accurate. So what people looked at as the next level was using some of the state estimation algorithms, which is where Kalman filtering comes into the picture. So everyone is familiar with Kalman filters. How many of you are familiar with Kalman filters? Sir is familiar. Okay. Madam is familiar. So some of you are actually sort of familiar. So Kalman filters, if you see, there are two things which are there. You actually have a model. So you come up with a model, and there are two aspects of this. So initially, you will define certain state functions, and then you take some data and then update it at regular points in time. So you have a measured update which is very correct, and then you sort of try to predict. So then there is a time-based update. So based on this, you try to track the state of charge of the battery. Okay. So basically this is how it is going to look. So here I have just put a very simple equation, equivalent equation approach of a battery. Okay. So a battery can be approximated by an electrical circuit also. This electrical circuit will behave exactly like how a real battery would behave. Okay. Why? Because the resistive component has been modeled here. Okay. And the dynamic aspect comes from this R1 C1, this particular branch. Dynamic means how fast it charges and discharges. And then the output of the battery is modeled by the EM-SOC term. So now, how to design a Kalman filter specifically for a state of estimating the state of charge of a battery like this? Then we have to model the battery dynamics. You can see I have a couple of equations for the state of charge of the battery. Okay. So basically what we do, we take these equations, discretize them, and then over a period of time we sort of measure the difference of, so we try to predict. With the prediction we have some measured data, we try to compare them, and if it is not matching we sort of update them. Okay. So this is the model. If you want to actually take a look at this model, we have this example here, non-linear state estimation of a degrading battery system. This will show you the proper thing, the process. So basically it has a particular block where we have a function where we enter the particular discretized equation. So we discretize the equation, I have written the equation as a function here, we call the function here. Give the initial part, the initial state, the covariance and all those parameters, and it should allow me to predict the state of charge of the battery. So this is just how it will, over a period of time, it will actually tune and it will estimate the particular curve. So this is one way we can employ. So this is like a Kalman filter, and this we can employ, and you can see in this case, particularly we are sort of able to measure it with some sort of a good accuracy. So as of now, this is a popular way, I mean the prominent way in which people are actually measuring the state of charge of a battery. Now let's find out how we can do the same using an AI-based method. So in AI-based method, we need data. Okay, so what is the data? Data we are taking three different parameters: voltage, current, and temperature. This we will use to train an AI model, and from that we will try to predict the state of charge of the battery. So this is how the end thing is going to look like. I'm just giving a snapshot in the end. So here if you see, this is the state of charge algorithm which is running, and ultimately we have an aim to actually run it with the hardware. So here you can see it has been implemented on a particular hardware, and we are running it in a PIL form. PIL means processor in loop. So model, we are generating code out of that. That code is actually running on your processor, and the BMS is actually running on the hardware. So the BMS is running on the hardware, and we have some data with that. We are trying to correlate and see how both of them actually compare. There is something very interesting that can be seen. We will come to that discussion later. Why? And maybe that is something that we need to think with. But this is something that we are going to build in the very end. So what is the workflow? Workflow will be different parts. So first part, definitely we will look at the domain specific toolboxes that will help with taking the data and using the data to come up with the right features. If you are building a machine learning model, getting the right features. If it is a deep learning model, then we can look at how we can actually create the algorithm. Sorry, we have to take it to the platform. So next we will look at the AI modeling. AI modeling, I will show you three different ways we can go about it. Firstly, we can build it in MATLAB itself. Okay. If you are starting out, let's say if you are trying something from your side, you can build it in MATLAB itself. Or if you have a very good model which someone else has built, maybe from different frameworks also, PyTorch, TensorFlow should be fine. That also you can bring it into the MATLAB environment. Okay, combine it with your model and deploy it to the different hardware. And this actually also happens a lot. Finally, we will look at simulation testing. So how to bring it into the simulating environment and doing something testing. Often we directly do not take a particular model and deploy it to a board. We have to ensure that the memory footprint is very small. So for that we do something like compression and then we finally deploy. So these are all the steps that it will take for the AI model for SOC, starting from the very base step to going to deployment. So do you want to go with this in a hands-on mode, or do you just want to, should I show you a snippet and then you'll try it in hands-on mode? Hands-on? Yeah. But I will give you a quick glimpse how it works and then we can try the same example in hands-on mode. So here what we are doing, if you are planning machine learning, we have created additionally two different features, taking that same data, doing a moving average with the voltage, moving average with current. Okay. Then we take the data that we have. Now we have voltage, current, temperature and moving average. This will be the predictors. SOC is going to be the estimator, response variable. That way I respond. So here also there are a lot of different methods which are there. You can actually, some come from machine learning, some come from deep learning. So we can look at some of the different models and see how the sort of prediction is affected when you use different algorithms. And then there are hybrid approaches also, where you can combine it with Kalman filters and what we saw before. Leverages both aspects, the prevalent one and then the AI related approaches. Okay, the first one, probably what we can look at is that how we can train in MATLAB's machine learning framework. Second one is MATLAB's deep learning framework, and third we can work with TensorFlow model. So this is how it will. This is the example that is there that we will look at. Okay, in MATLAB's machine learning model, it will look like a script which is there. So first we have to access the data. It's quite a big data set, by the way. I hope you will be able to download it. Okay. So once you have the data downloaded, then you can look at the data also. What is the data that we have at our end? So we can look at the exact data in terms of plots and all. Then we can go and use the machine learning app. So we have an app where we can train the whole algorithm. So here you can see it says regression learner. Okay. So you just open up the app and bring in the data. So from workspace, whatever data we have downloaded, we will be bringing it here. Identify the approx, the specific validation pattern that we are going to do, and then we can just start it. So what you have as a benefit in the regression learner app is that in one go you can train with or different sorts of models all in one go. So here all quick to train means you can train a lot of different AI models and try to see which one performs best. So in one go it has opened up a lot of different models, linear regression, trees, different sort of other models, and then it is training it at one same place. And once it is trained, you can see the accuracy of these different approaches in one place. And then we can, if needed, we can take the test data and the trained model and then take it to the workspace. We can do testing also here. So here we are just taking the same model, trying to test which one is working better. Once we do that, then we can export it to the workspace where the next step will happen. So this is the workflow for the first and second part, where we have data, we are accessing the data, and in the second step we are training the algorithm, and then we can test the algorithm for different sort of temperature ranges. One very interesting thing that you will see here after testing is that you will have a graph that looks like this. So the blue curve that you see here, specifically the blue one, it is the data that we have for testing, and orange one that you see here is the one that the machine learning model that we selected or we showed predicts. So any interesting observation that you see here? So you'll see that it doesn't have a very smooth thing when it comes to the discharge curve. You'll see a lot of fluctuations which are there. So it's not that accurate in tracking the discharge. But what about the charging part? If you look at the charging aspect, if you see, the fluctuations are less. So something for you to think about. Why is this sort of behavior there in the trained model? It is not there in the data that we are using for training, but it is there in the trained model. So I think this is the right time maybe to look at the hands-on approach. Should we try hands-on?
We can connect with network. If I is not, we have to download models from the apps.
Okay, we'll try it. Let's try from our end.
Now only will do. बोलो
So we'll take a quick break for a short while.
Sure.
Then we'll
So all of you assemble back within 10 minutes. Don't take much time.
this is some
It's hands-on, so that will be here.
So please come with your laptops, then it will be useful.
I told you about BSc to come. Triple E.
How many can you do?
Don't take. Just coffee. Coffee and coffee.
Madam, this is back. 127, our students are reflecting, sir. 5 is missing. I will contact them.
You got the login?
List they were sent now.
They said no. But they told they will be giving you the login credentials.
Login credential they have not given, sir. Only downloaded list they have sent in the group.
Say they have sent the VT. Come.
Because region wise they are doing it, seems it will take time.
Nowadays, it has to be very easy. Stop.
Then you take this service.
I just good.
Just you take this.
Thank you.
No, sir. Thank you.
Good. It is good to know there is a battery course also which is there.
Yeah. Oh.
Because you have a lab, I see. So
So actually EV related, they have 3 courses. One is the fundamentals of EV baptism. So there we discuss about battery modeling, all this battery. They have a course called battery management system. Separate for the battery management system. So there they completely discuss about the depth of then the advanced course like EV and hybrid. So there, because the connectivity is required for that subject mostly on the powertrain system and all battery stuff related already.
So whatever we will cover today might be a bit relevant to the
Yeah.
management
Yeah.
system. The students actually look
Anyone is ready? Students. Right? What's the final result?
Communication,
You should be small bets this time. But if you miss the initial companies, then you will later. Okay, all the initial companies, it's all good companies. Okay. So don't miss it, and you know, already you have attended, you have that experience, right? So with that you just see what else is required for this interview. What happened with the result? Very technically people are missing. It's a software company. What they asked? Don't say if you are having good skills, then they will also take you. Okay, so just see that. That's right. You should not tell my parents will be happy. First, you have to say you are happier. I will be very happy.
I call my parents, how I should respond to them.
So tomorrow will be a holiday.
Yeah.
Concepts from content development team. She's faculty.
Are you an expert? Everything is not I will answer. You will also. No, if they say one should be present, what? You can't prepare today. Okay, Mata. Then come. I'm coming. 1 minute. Internship, please. Have download பண்ண
So if you're able to open it your end, so this is the example that we'll go through. So you can open it up online also. I mean, it's available online. If you just search by this name, predict battery state of charge using machine learning, just plus add MathWorks, or you can search from the MATLAB website also. So this will be the example that it will take you through. So command window, if you want to open it from the install version of MATLAB, you can just copy the command. If you see the name here, if you type in the command window / predict pattern state of charge using machine learning example, then it will open up in install version of MATLAB. Like I type it here, it opened up for me in MATLAB installed one directly. If you do not have MATLAB installed, that's fine. You can open up in MATLAB online. Yes, you can open up in MATLAB online also. So you can open up either in MATLAB online. So then this is the blue one. Or if you open up in MATLAB, then you have to just copy the command and put it in the command window. If you want to open it up online, it might ask you to sign in. That is one thing that happens. If you have installed version of MATLAB, then it's not a problem. It will directly open up there. Yeah, so that will be network dependent slide.
Copy online is there, otherwise online you can copy command.
You just type the predicted line in Google.
So what we believe from our side in the future, a lot of things will be happening in the cloud only. So that's why cloud support has been becoming very important. But then network bandwidth becomes the bottleneck sometimes.
The battery SOC.mat file and
Yes.
predict battery SOC.
There will be 2 files. That's correct. So, it open?
the upper command is not taken.
It should be there. If the page is loaded up correctly, it will be there.
मैं तो चीख ना दे पड़ेगा कि नीचे ले रही हूँ माटी उड़ गई मुझे
After copying in
I'm getting this screen.
यूज़ பண்ண
So this example, if you see, there are the toolboxes that the users have mentioned here. Statistics and machine learning toolbox. If you want to do trading and want to do it very fast, then you take use of parallel computing toolbox. So basically the process that we are going to use is that we will first take the data. Okay, so loading the data is the main step. So many times the major challenge when it comes to working in the battery domain is actually getting the data. So from our experience of working with different users, the main challenge working with batteries is that getting data. Many people want to work in battery domain, but access to data is challenging. So MathWorks has collaborated with a university in Canada called McMaster University. So they have actually given us the entire data set, and MathWorks has made it public. So you can go here, and if you want, you can take the data and download it. Okay. So this is the process. You can actually download the entire data set and prepare the data set to create the subset. So what we have done, we have already created a data set for you. So that introductory part, you remember the introductory part where we talked about that first step is accessing and working with the data. That part has already been done. Okay. So battery dot all the processes that you have to do with data, it has been done, and this file has been made ready for you. All we are doing at our end is loading the data file, observing what the data set is, and then training our model. So as of now, if you see what we are doing, we are just taking the data set, training data set. It has data at different temperatures, 10 degree, 0 degree, so I think 10 degree negative, 0 degree, 10 degree positive, and 25 degree. So Canadian people have done experiment, they have taken their conditions into consideration and accordingly created the data set. So if you see, this is the data set which is there. What we are doing, we are loading those specific data sets corresponding to these temperatures and giving it certain names. Okay. Then we are looking at the head. Head means the top column and sum of the data set. So if you do head training data, it will take the heading of the different categories which are there and show you the first 10 data sets. Okay. So what is the data we had here? Initially, if you look at our model, we had from McMaster University voltage, current, temperature. Because we are doing machine learning and machine learning works best when you give it certain featured data sets, we have created two more features: average voltage, average current, and what we are going to predict is the SOC. So this is the data set that we have. Okay. So if you have opened it up online or if you have opened it up on the MATLAB, so I have opened it up on my MATLAB. So here the files are only two. So I think at your end also you should be able to see two files. This is the dataset file and this is the main screen. The first part has already been done for us. The data has been made ready for us. If you load that particular mat file in your workspace, you will be able to see this particular file. Okay. There is some testing data: 0 degree, 0 degree, 25 degree, 10 degree. I have training data. So training data is there and testing data I have. So what will I do? I can actually first take a look. So the script actually takes you through step by step. So first part is actually loading the data. Okay, the data has been loaded. I am able to see the head of the data set, so I have just executed it. You can execute it by clicking the blue bar, or at the very top you can do run and not this one probably. So I think better is to click this blue ribbon. It will only execute this section. I can see the data set and then I can do some plot. So variable, we have an interactive plot here. You can go here and plot different parameters. You can plot voltage. You can see the voltage profile here. You can see the training data. A lot of data points are given here, and then data at different temperatures I am segregating, and I am just plotting the data and see what the values are. So it's an interactive way in which I am coding. I can see voltage, I can see current. Okay. So it is good to understand how the data set looks like. So this is test data specifically for current. Apart from that, I have temperature. You can see the test data for temperature. What else do I have? I have average voltage. This is an interesting thing to see. Can you see average voltage and compare it with what you saw for? I had a question in the very beginning. If you look at the results, I will pose the question once again. Look at voltage data. Look at voltage data. Okay. I can probably explain it also. So this window, if you want, you can open it up as a new figure also. And just look at this aspect. So this is the discharge profile. If I maximize it, you get something like this. If you look at the charging profile, it's smooth. The charging profile is smooth. Discharging profile, it's not very smooth. Okay. Now what we are doing, so this was just voltage. Now please take a look at average voltage. Now look at average voltage. There is some sort of an average happening, so you don't have that much vigor in this line, so fluctuation is less. And this is very important because how good your data is actually reflects in how good your model actually is. Okay. So data access and visualization of the data part is fine, right? So now we can go to the next part where we will train an AI algorithm based on the data set that we have. How can we do that? We will use an app to do that. We will use an app to do that. To go to the app, I will minimize this one. I will go to the very top part, apps. So what I am going to use, I am going to use a low code approach to train my model. I will go to apps. So apps you will find in the main MATLAB tab. This is the MATLAB main tab, main file, main window, where you see home, where you see plots. This is where you see apps. I am going to look for a particular app known as, either I can go for specifically we are going to predict a certain trend. So there are a couple of apps here: regression learner, classification learner. What we are going to use here is the which one?
Regression.
So we are going to use the regression learner app. Okay. So we are doing slightly different from what you see in the script here. In the script, if you see what they have done as a next step, once they have the data, they have used a Gaussian process regression model. This is what they have done. They have done it using writing some codes. See, they have done something by writing some code. We can avoid this, we will try something else. Okay, we are not doing this one right now. So we have opened up the regression learner. So app will be called regression learner. At the very top, you will be able to see the name regression learner. So first step first, we have to bring the data here. You can go start new session. Where is our data? It is in the workspace. So I can do start new session. Regression learner. Just below that, we have start new session. Start a session by selecting data from workspace. So it will open up something like this. So I hope everyone is here. After that, we will go to the next page. No? If you have any challenges, let me know.
After regression learner here.
So regression learner, are you opening it up online?
After selecting, clicking, it's not coming.
Which one? It might open up somewhere else also. It's an app.
I know, sir. I opened that, but it is not necessary.
Is it the online one?
Online.
Okay, it hides somewhere sometimes. Online one hides somewhere.
You can also open online.
Isn't it this game?
Sustainability already open on that.
No, those are
No, that's it. You cannot do it. You are doing working, so that is also many tabs already open and but you don't have anything more. New session.
So it's taking place.
It's taking time because of the lag. It's because of the lag it's taking time.
You are using the 2024 version, sir?
I want 2025A.
2025.
So online also, if you are using it, will automatically take 2025A because online one gets updated to the latest one. So I'm using 2025A only. So I go to new session from workspace. Then select input. So in select input, you can see all the data that you have at your side. So you have to use the training data. Yeah. You can see here the name will come training data. Can you see the name training data?
So training data is already available in your workspace.
Yes. So the introductory part where the data preparation is there, that has been separately already taken care. So if you have opened up the example, if I just show you this part, okay, so we have directly started with the training the model part, but if you look here, there was an additional part at the very beginning which talked about data preparation, download and prepare data. So if you want, you can go and you can open up. There it talks about the entire part where you go to the URL where the data is. You download the full folder of the data. Okay. Then you unzip the data to a location. Then you take the folder, the full file, and create train data set, test data set folders, and then take the data and put it in those particular locations. So data preparation part I actually skipped. So that is a good point. Madam said that how does the data suddenly come in? Once you do this part, then you have the data at your side. So this was the part which is already done by somebody else.
What data is that, sir? Which you are going to upload?
What data?
What kind of data?
So if you look here, the data was taken from a particular university, McMaster University. Basically, it is what they have done. They have taken voltage measurement, current measurement, temperature measurement, and SOC measurement of a cell, of a lithium-ion cell. So if you want more details, you can actually look at their location. They have made the data public, which is a very good thing. They have made the data public. You can use it for your research purposes also, it should be fine. So this data, what additionally has been done, it was only voltage, current, temperature and SOC. We have created two more features, average voltage and average current. Why? Why did we create this? We just give it two more features. Why? This is what domain engineers should understand. Yes, ma'am?
So in theory,
Constant
also-
performance, like,
But looking at the data, what do you think? I showed you something interesting. Average current, if you see the average current, or just look at the average voltage you saw, just look at the normal voltage. What do you think?
those spikes.
Yeah. So we are giving it a feature which is smooth corresponding to the original feature. Much more smooth. Okay. So with that we are training the algorithm. Okay. So this is where all of us currently are. Okay. So that data, whatever data was there, that training data we brought to this particular environment. So set variable training data that we selected. Okay. What are our predictors? Our predictors are all of these parameters. So these are predictors. Using this we are going to predict. Apart from that, we can do cross validation and all those things we can also do if needed. Right now I will just let it be, just to get a feel about how we do the machine learning thing. So once this is done, we can actually start the session. So it will open up a window where it will plot the response plot for the predictors. It will plot everything and it will show me something here. It will give me some summary here and we will get a response plot like this, something like this. Now what is very interesting about MATLAB and Simulink is that you can train a number of machine learning models at one go very fast. Okay. You can train a number of models very fast here. How do we do that? If you look at the very top, you don't have to write any code. So there are a lot of different models which are there. Where are the models? Typically the models are given here. Some linear regression models, some regression trees, some support vector machines. Okay. Different models are actually given here. What I can do, if I want, I can select different sort of models here. Maybe I will just put something like this. So you can select and keep models. You can select and bring any model which you think would be useful for your example. Okay, you can select different models and keep it here. Or I can also do this thing. So there are some models which are very quick to train. So if I just want to quickly see, I can just go for all quick to train models. So now I have multiple models here. I selected one on my own, or I can do multiple quick to train models also. Done. Then what do I do? Then I can go and start training. So if you have the use parallel option on, it will try to use the parallel processing capabilities of your laptop only and try to train it. So I can train all, or I can train selected models also. So let me just train all and just see what happens. So I'll just let it train all the models. So it is opening up a parallel pool on my processor, computer, laptop, and it is going to train all the models. So you can see the training happening here in the left part of the window. And then it is plotting different sort of response plots. So now training is happening for me. Whatever I selected, it is sort of training all of them together.
Yeah, because I'm using online.
But what you understand from this graph?
So basically response plot means that see there are two things. Okay, one is the predictor. So there are certain parameters with which it is going to predict, and so response plot typically means that how well it is able to correlate to the data that I have corresponding to SOC, how closely it is able to map onto the points which are there. This doesn't help me a lot in this particular case. That is what I agree. For this particular case, it doesn't help me a lot. What is going to help me right now is this particular parameter, which is root mean square of error. So for the predictions, it is calculating the root mean square of errors, and the lowest root mean square of error means the close I am to the predictions which are there. But this I am actually validating that which model is better for me. So right now from this particular example, it is saying that the tree model is better for me. You can maybe try with something better and see if you can get a better root mean square of errors. Okay, that you can try out. Till this it is works well for everyone.
That RAS will be same model as right now. Depending on your training.
We can choose
This automatically, this also
Specific
will
thing.
take
This which is not supporting in my offline. So the main predict matrix of using learning
and
based
you have
on
to type
You can select any of the models and you can just play it there.
but it didn't took for me. It is given some so I went to
we can choose one by one.
But you can't write this. Then it will take all the
If
Which prefers the
statement. So that it will into the machine learning.
no.
There is also this plot. I am not sure, I have not tried this, but you can try this one also. Probably this one will be interesting.
Train the data. Predict through. We should know the paths how we are going.
It is sort of trying to give the perfect prediction, and it actually shows the spread of predictions and to response.
Meditation.
So typically after this, any model which you think is going to be useful for you, let's say for me the tree one is better. So what I can do, I can select that particular model. Let's say the tree one is working well for me. This I can export back to MATLAB. How can I do that? I have selected that model, whichever one is better.
Better meaning like the
Compared to the others,
RMSE value.
yeah, RMSE value I am comparing. So this one seems better.
Yeah, it's same actually.
So I can go to the very top. Either I can generate a function. If I generate a function, it will give me a code. So next time, I will not have to do everything. I can directly open this up, or I can export the model only. So I can export the model to the workspace. I can export the model directly to Simulate, or I can export the model to Coder, depending upon what my end goal is going to be. So right now what I am going to do, I am just going to export the model to the workspace.
3000. This is a workspace.
So at the very right hand part, there is an option called export. This is where I can go and choose the export option. So export model to workspace. If I do, it will ask a name. So here my model name is trained model. Maybe just to ensure that I don't overlap with anything I previously trained, I am writing trained model SOC. And during export, it is also going to include training data in the exported model. If I do OK, then it is going to export the trained model to the MATLAB workspace. What many people also do, that this model might not be a very optimized one. You can create something like an experiment where you can modify the training parameters and try to improve the accuracy of the model that is there. We can export it for deployment to a production server also, which is something business people are interested. I can export the model to Simulink also. I'm just showing this, not needed. Even I have not tried it much. It's almost. So if I do it, it can also take the model directly for me and directly open up the same model and integrate it with Simulink. So you don't need to do this step. I am just showing that it is possible to take a model and export it for Simulink also. We do not need to do always. There can be instances where I don't need to do this explicitly. I can go to Simulink and import it also. So here what I did, I took that model and imported it directly to Simulink. If I go inside, you can see how it actually looks like, or if I can go and click here, you can actually see that the model that I created, that particular model is actually loaded here. So here if I have created a battery SOC model, I can take this and I can couple that with my SOC model directly. So this part is done. Let me do one more thing. I have just done this. If I am able to do this. So here I have a small bit of code on testing against the data set. I think this is train. So I'm just opening up how the model actually looks like, the trained model. So this is a trained model SOC that I created. Okay, so inside it will have a predict function. Some variables, it tells what is the required variable it has. It tells what type of model it is. It also talks about this is a trained model exported from which version, and then It also talks about how to predict. Let me just try to see if I'm able to just. Are you getting the same sort of an error here in prediction? I think they have saved the previous one in some different way probably. Okay, it's because of this thing that error is coming. So MDL is actually the training data that is there. That data also it is sort of calling here. That's why this particular error is coming. So it's a model object that they have created for the training data. Okay, right now we will not worry about this one. So we will look for the prediction in one more different example. Because here what they have done, they have taken the training data also and they have used it in the model. So that is what they have done here. But one common thing we will see here, specifically for the example that we have done here, if you look at the example that you have in the very end, you should be having this sort of a pattern. So you get this sort of a pattern here. What I want you to notice is that if you look at the discharge curve, you will see that there is a bit of fluctuation which you see there. You can see it in the discharge curve, but in the charging part you will not have this fluctuation. Okay, so this feature will be there in the data set which is there. So right now what we did was that we took some data, we were able to train the model and we were able to take the trained model and bring it to the MATLAB workspace. So all of you were able to get the trained model at your end, right? We will see the integration part in the other step. Now apart from that, what we can do here is that we can use the deep learning framework also to train a model. So this is going to be the next example that we will use. Okay, this one. So again, just to show, some steps are going to be the same. So data preparation, same data we have. So we are taking the data. Okay, then we will load that particular data, and then we will try to create the deep learning model. So deep learning model, what we can do, we can actually, if needed, we can actually create it by command also, or we can use the app-based method also here. So if I use app-based method, instead of the machine learning app or the regression app, we will have the deep network designer app. So in deep network designer app, have you used this app before? So So here we can create an entire algorithm just graphically. We can drag and drop different networks and create the entire algorithm from scratch. We can analyze whether it has any errors. If it doesn't have any errors, then we can take this particular one and then we can export it to MATLAB. So we can create any sort of deep learning algorithm very interactively, export it to the workspace, and then we can work with that.
What is the name of that?
It's called Deep Network Designer. So it should be there also.
So when you click on the icon for the MATLAB, directly we can go to the app on the home page.
Yes.
There itself, all the apps will be available, right?
So one can go that way, or you can also do type in the command Deep Network Designer, it will also. So after you have created the models, we can go, we can then start training.
Deep network design.
Second one. No, it's not that one. And this is a different.
So these apps are available only in 2025 version or any the previous versions also?
So it is available in the older version, I think.
2022 onwards it was.
2022, even 2019, I think it was there.
But not this much.
19 we have, no, but it's not integration is not very good.
So I will show you where the example for number 2 is located. So very similar to the last example, we can locate the example at the top right. If you see, train deep learning network for battery state of charge estimation. It's a pretty long and thorough model. You can get it by this particular name. So this is the name, train deep learning network for battery state of charge estimation. So this model, if you see, it's a very thorough model. It actually starts with requirements, preparation of data, training, testing, integration, and code generation. I have jumped a couple of steps, so that's why it shows step 3, but actually it has a couple of previous steps also. So if you open up, it might open up on step 1. So first one is actually defining the requirements. So this follows the model-based design approach where you start with requirement and then it goes up in code generation. So you can directly take this example and map it to model-based design, which is what the industries do. So if you search by this name, it will take you to this page. I skipped a couple of pages just so that you don't have to go the model MBD path. Just to give you an overview, like requirements means that what this is going to do in the very end. So typically industries go by this path. So if you see here, they have certain requirements that they will club with the modeling process. So that part is given here.
This is since 24B minus 24A.
So this is the first step, like industries will go this way, then they will go with the preparation of data part, which is also something we just sort of skipped today. So same process, like taking the data and then creating this sort of training data sets.
But here the average value of the voltage and current is not. Only the raw values of the current.
The question is why?
No, the average
Like,
value
it's not
every
there.
time there are spikes to smoothen it.
So that we need to smoothen up the data so that eventually when you have a trained model, it will not have that much of a fluctuation. If you don't put the averaged one, if you then generate the model, it will have a lot of fluctuations during discharge. So we had the averaging on the data set done so that when you create a trained model, that fluctuation will not come into that the fluctuation characteristic will not come into the model that we are training. Deep learning is something different. Deep learning, we do not need to explicitly give it features. It will automatically pick up the features. Okay. So deep learning, we do not need to give features. That's why we do not have that extra averaging step here. So we have temperature, voltage, and current.
So the previous one we have done machine learning. This is the deep learning.
Yes. Previous one was machine learning. Okay. This is the deep learning one. This is all good. So at your end, if you want to download this particular example, then couple of ways you can go about it. You can actually go to the very top and either open it up online, or you can copy the command, which is what I am going to do, and I will open it up on MATLAB. Before that, I will clear everything so that the previous things are not there and there is no confusion. So I have just done CLEAR and I have cleared everything so that everything starts from scratch.
Okay, we are collecting the different voltages, currents and the temperature. Then we are training the model. Then what's the outcome?
Then it will do prediction for us.
Where can we see the SOC?
You have to give it 5 parameters. If you give the 5 parameters, then it will predict the SOC.
Can we see anything here?
We can actually see.
Like whichever the graphs you have shown, those are like the predicted value and the true value and the error it was showing in the previous
color
graph.
indication is there.
Correct. So how much is the SOC? How will come to know from the graph? Or any other thing is there?
RMS is there, no?
Huh.
That is the average for different regression. So that is average. You can go with the testing also.
Okay.
That separate option is testing is there. There you can upload all your data to test.
So here in the example, the very end part, this was like visual testing, like we are just plotting them together. That part was there. I was not able to plot because I think I missed adding the. Now I added the training data, but I did not pass it as an object. If you pass it as an object, then it will sort of show you something like this. But this is a visual confirmation, it doesn't help much. So that's why in the very bottom, we were just comparing the RMSC for different temperatures for the predicted model. So RMSC 10 degree means taking data for 10 degree, the actual one, and comparing with the model that we have built. And we are able to see this error plots. So this tells us that which the model is, what sort of error it has for different temperature also, that we are able to compare here. So maximum absolute error and RMSC, both of that we have plotted here. So very interestingly, same model that you are training, it's one model only. We are passing it 5 different things, but prediction it has for different temperature. Accuracy is also variation is there. So for 0 degree, if you see, it has the highest error, but 25 degree the error has come down. Now we are taking the same data set, but we are going to train a deep learning model. Same data set, deep learning model, we do not eventually have to give it any features also. So here there are 3 things: temperature, voltage, current. No sort of averaging we are having to do here. So this is the example. I am going to now just open up the example at my end. So let us open up the same model. So first part, as you see, is the data preparation part. It talks about the whole data creation aspect. So what we are doing here is something interesting, I believe. So here what we have done, we have taken the entire data set. So we are just loading it just to view the data. So this is how the data set typically looks like. At each temperature, we have this sort of a thing. It will have, there is a X variable, there is a y variable. So basically, there is a each temperature data with predictor and response variable. What will be the predictors? Predictors will be the things that we are giving as input, and SOC will be the thing that we are estimating here. So that will be the response which we see. So we are combining. If you see, there are 36,000 into 3, so that is the input variable, and SOC is the y variable which you see here. This entire list of values, this is the SOC. So what we are doing, we are combining 4 temperatures into a single observation here. Combination of that, and we are sort of plotting it all here. So this is where we are plotting the values for temperature, voltage, current, and the SOC. So this is how the data actually looks like. So we can see the discharge curve here, and then the charging curve, discharge curve, and then the charging curve. So look something like this. So this is the SOC, how it changes, and this is the 3 different temperatures. The temperature, voltage, current. Temperature, we have 4 of them. We have combined everything, and we have plotted them all together here.
Can you zoom it side first? Because the voltage and current are overlapping.
Yeah, so to zoom, you have to go here, and you can just. But I don't think it will help us a lot. What you see here is actually very interesting. If you look here, if you look at the current curve, you will be able to see the discharge pulses which are there. Can you see these pulses?
Can you further more zoom?
So these are the discharge pulses, the one that you see in current. So what happens during experiment is that to understand this sort of dynamics, do you see the yellow pulses? So what are this? Current. So what we do here, to discharge it at a given point in time, we have to take a small amount of current. Okay. So there is a equipment known as, I forgot exactly the name of that equipment. What it does is that at certain points in time it will start drawing current, then it will stop. Then it will start drawing current, and then it will stop. And then we will have the voltage curves here. You see this voltage response, I think in red. These are the sort of curves that you have here. There is some sort of fluctuation because this comes from the measurement. Okay, the yellow one that you see here is the impulse. So we have an equipment that I know draws this amount of current at a given point in time. So this is known. This is coming from the equipment. And these are the pulses that you get here. These are the measurement. That's why you have a bit of fluctuation there. So this is the voltage curve. This is the current curve. So this sort of curve, whenever you talk with any battery manufacturer, they specifically give you this particular data. Okay. So this is known as pulse discharge data. There is a term for that, I don't remember exactly. So if you ask a battery manufacturer for data with that particular term, they will give you something like this. So this is the raw data that we have at our end. So there are some data preparation steps here. So typically these are the things that typically I don't go into. So it is more about taking that particular data set and sort of modifying it so that we can train our deep learning algorithm. So here we are preparing the data for training an LSTM deep learning model. So how we split it into chunks and combine them. Most of those aspects are covered here. So after data preparation, I believe this is what it is sort of going to look like: temperature, voltage, current. You will see something like this. So then the data is now ready for doing the deep learning model training. Okay, so then we can go to the training aspect. So at our end, mostly if you see us, we focus a lot on the creating the algorithm. But typically when it comes to industries, they focus a lot on the data preparation aspect. That is why this model gives you this end-to-end, this whole workflow, starting with requirements. At academia, we are not much into requirement, but industry will have certain requirement. Then they will go into the preparation data. Then they will go into training the model. But I just wanted to give you some hint like how the data actually looks like in the very raw stage. And then people actually modify it a bit so that when you train, the training accuracy actually is going to go up. If you just train with very raw data, the accuracy of the model is not going to be that good. So this is the second part. This is where we actually train the algorithm. We have access to the data, so now we can go and train the algorithm. So there are a couple of ways we can go about it. So here, let me just open up this training one. I think this will opening at my end. Maybe I'll just take you through the whole thing. So there are two things we can do. If there is somebody, let's say, who is expert in writing code and understands deep learning models, they can actually write the code and create the entire model. So basically we are just loading the code training data here. In network architecture, what we are telling it that the number of features that we have are 3. We have 3 features, right? Voltage, current, temperature. Response variable is 1. How is our network going to look like? If I write it in code, this is how the whole deep learning network is going to look like. It will have certain layers. First layer is sequence input layer. Second, we have an LSTM layer, a dropout layer. Then one more LSTM layer, one more dropout layer, a fully connected layer, and then a sigmoid layer. Either if I run this code, it will actually create the entire algorithm, entire network for me just from commands. Okay, let me just do it just to see. If I do this, it will create the entire network just based on the inputs I have given here. How do I know? I will have something called layers in my workspace. If you look into the MATLAB workspace, I will have something called layers here. So this is the network that was created. Alternatively, I can do the same thing interactively using a interface where I can visually work with the network. It's known as Deep Network Designer. So now I'm opening up Deep Network Designer. It is slightly busy. It will open up an interface called this Deep Network Designer. Now this is a very good way where I can actually work with a lot of networks. I can create one from blank, from zero, which I can do in a bit. But let's do one thing. Let me take the one that I just created programmatically. I created one by running that program, right? It is there in the workspace. If I want, I can import that. So I created layers. If I just import that, it will open up the entire network here and it will look like this. This is what I created. This is going to look like this. So you can actually import any network and you can visualize how the network looks like. If you want to build a network, that also you can do. How? Here I know first layer is a sequence input layer. So I will just go to sequence input layer. I will drag this in the canvas and put it here. That is why I built it, just for reference, so that I just don't have to go to script each and every time. If you want to build it from scratch, you can build it here. Okay. So here I will tell that what is the sequence input layer. It will take in 3 inputs and minimum length is like 1. So here I have to go and change the input size to 3. Then I have an LSTM layer. Where can I find LSTM layer? I can go into the layer library. In sequence, I can find LSTM layer. Bring it here. And LSTM, what is the property I have? So number of hidden units I have is 256. Activation function is tanh. Sigmoid is the gate activation function. I'm not sure what are the things that it will ask me. I think this is something I have to change here. Number of hidden units I have 256, so that I will change here. Any questions on this? The remaining things I think are all same. Dropout layer, I will take a dropout layer by, if I don't know where the layer is, I can search in the filter layer tab also. Dropout. So I can see that that layer is there, I will just bring that layer here. One more LSTM layer. One more dropout here. A fully connected layer. And then in the last we have a sigmoid layer. So feel free, try that at your end. I think this is a very nice intuitive way of working with these networks, and you can just combine all of them. Just it's drag and drop. So like this you can create your entire network from scratch. I can auto arrange everything and I can analyze. If there are any errors, it will tell me what errors are there. Chances are that it will throw multiple errors because I have a couple of networks there. There's some warnings, it has, okay, no warnings, no errors. So one thing that you can see here that it also talks about how many learn levels are there. Because I have a couple of networks, it might show a lot of learn levels, but I might delete the one that I created in the end, and now if I analyze, it will tell me the exact number of learn levels. So almost half, 463 learn levels. It also talks about each of the layers, what are the layers which are there, and talks about the parameters of those particular layers, inputs and weights and those things. Once this is done, then I can actually go and export that to MATLAB. So it is asking me for a name, net_1, so I can do, if I do OK, it will export that network to the workspace, net_1. It has exported to the workspace. So this part is done. So after this, after doing this, then we can go and train this particular network. So if you see here, we have the training options which are there. So there is add-on, a training network using optimizer called add-on, and then initial training rate and all is given. 0.01 is the initial learning rate. How many epoch, how many times you train using the same data? That is 150. Size of the mini batch is 32. Okay. And then we can see how the whole training actually happens here. So training options we have mentioned, initial learning rate, epoch, so all of those details we can give and we can start training here. So in MATLAB, the function that trains a particular network is known as train net. So to train the network, what we have done is that initially what we have done, we have made the training as false. If you mark it as true, it will start training the network. Else we also have in this example a pre-trained model which is there, which we can directly start using for predictions. So what we can do, if we want to see the training, we can make the do training as true. So then it will take the train net command. So train net command is the one that trains, This is the data set, X train, Y train. Layers is the name of the network. I think I have changed it to net_1. I can make net_1 also. And then the different sort of options which are there. If I run this, it will start training that particular network. So without parallel processing, it takes a certain amount of time to train. I think with GPU it took us something like 3 minutes, I think. So here it has started training, and you can see how the training is happening. It takes a certain amount of time. That's why we also have a backup model which is there, which is already trained for us to actually just look at the predictions. So should I stop this one? I'll just stop this one.
So your laptop processor i7 processor?
Yes. I think I have something like, I'm not sure how much RAM I have, but it has
16 GB.
either it is 16 or 32, something like that.
Minimum 16 required for this laptop.
For training and all, I think RAM might not be the right thing to actually look at, because when you train deep learning models, the training can be parallelized very easily. So GPU computing is the actually right resource. So typically I'm not in MathWorks, I'm not the AI person, I'm the electrification person who also does AI. So integrating AI in these sort of systems. But for our team persons who actually go to the field and show AI examples, their laptops have GPUs. So their training is actually very fast. So if you have a good GPU, then this sort of training, you saw it like it's just 3 minutes. You can do end to end. In my laptop, it might take, I believe, a longer time. It will take something like 15-20 minutes. It will take.
So consequently, whether it will affect the performance of the laptop over time if you keep on using for this heavy resources, whether it will affect the performance or it's not like that?
Effective performance
Of laptop over the time if you keep on using with this heavy training and also, whether it will affect the performance if it is some i5 processor or 8 GB RAM like that.
The only thing that you have in terms of trade-off is the time.
That's it.
Yeah. So if you have a, also in this particular application, what we are working on, if you look at the data, it is basically sort of the data that you see typically it's like specific data points, right? It's not that heavy in parlance of AI. There are people who actually work with specifically image data set and all. For them, it will be very heavy load and it will heat up also a lot. But this, in terms of computing, it's less, not that much, but it's a longer time it will take to do. It will not affect it. Time will be consumed more. So I will just close this. So if you do the training as false, then what it will do? There is a trained model which is also there just to save time. It will load that trained model here, and it shows you the training that it has done before. You can see that training here. And if you look at the hardware that we have used here, it's a single GPU that we have used. So just with a single GPU, typically you can have the whole training within 3 minutes. Nowadays many laptops are coming with GPUs also. So once you have this thing, then you go and look at the compare. So here I don't think we are going into specifically the testing aspect, that is in the separate script. So when it comes to industries, what they will do, they will check everything within certain requirements. So in industry they will have certain accuracy related requirement. They will compare with that and try to see whether those things are met here. So what will be the third part? So third part specifically, if you look into this particular example, so the best thing about this particular example is that it takes you through the whole workflow step by step. So now we will go to testing the model. Okay. They have not gone into testing, it goes into comparison interestingly. Okay, sir. Now the main question is that after training the model, if you see there is a sub branch, someone might go through this, someone might not go through this. When will you go through this? When will you not go through this? Compressing the model. Okay, what exactly is compressing the model? What exactly is compressing the model?
If you deploy it somewhere, area shots will always better.
That is on the money exactly. Like when you deploy it, the size should be less. That is actually true. So whenever you have this sort of models, there are a lot of things that are there. Firstly, it comes with some trained data. We might not need for deployment. So we take that out. There are models like this which might have a lot of branches. Some of that does not need, so we can prune the model. So there are ways in which we take the same model and we reduce the size. One thing is also like you can prune. So pruning means if there are additional branches, any repeating structure, we can take that out. Not needed always. Then projection. So using some sort of projection capabilities, we reduce the number of learnables. What we try to do after taking the original model, we prune it, then we are projecting it. The root mean square error is a parameter we use to compare. It should not change a lot. Accuracy should be high. So after original, if you prune it, the number of learnables are getting reduced. Okay. Then if you prune a project, it is reducing further. So overall, using this process, we reduce the size of the entire network. Then we take this, and then there are compression can be just not one level. There are multiple levels in which we iterate and we try to compress it. So there are multiple levels. So we can create different sort of mini batches. Take the same network, again do the same processes and try to see whether we are able to compress it further. So this part is covered here in detail. The reason is that industry is actually very much interested in compressing it. So you can see we are over a period of time we are trying to reduce the learnable. So learnable we are reducing, but after reducing learnable to a certain level, we will see the error has suddenly shot up. So this is where you have a trade-off. So you know that you can only compress it until so far till the error starts increasing. So you only have to go and stop somewhere. So that is something that we are able to compare by getting this sort of graph. So then in the end, we take the original network and compressed network and we try to compare the RMSC, original network and projected network. If the error is less, then it's fine, we can take this one and then we can go to the next step where we do the testing. So here also we have taken, they have taken the same network and they have done some sort of a prediction at different temperatures. So if you want to do it at our side, we can actually copy this example and try it out. Or we can go to the next step where we test out this particular model. So do we go through testing? So there are two things that they are using here. We will be primarily using deep learning toolbox. What industry also does is something called verification. So there we have a deep learning toolbox verification library also. So you are able to verify whether that network whether the trained network meets your requirements or not. So I'll just try to quickly take this example and open at our side. So please feel free to explore and open it at your side. So basically in the very beginning only they have shown the true and predicted plots. So the prediction is done at different temperatures, 20, 0, minus 10, 0, 10 and 25. So just loading the test data here and then taking the SOC, predicting the SOC using mini batch predict function. So there is a function that allows us to do prediction in terms of different mini batches. So that is what we are doing here. So this is the data. So we are loading the test data. And we are calculating the RMSE, and then in the next step we are just plotting the residuals. I think already it has plotted based on what was there before. So for the 4 different temperatures, it is taking the network and it is trying to predict and comparing the accuracy. So same thing that we saw before, similar thing we see here also, like specifically for 25 degree we are getting 0.03, okay, and for 0 degree around 0.031. So RMSs are as per whatever we have seen before, similar sort of RMSs we are seeing here also. So whatever model we have created, in testing also it is sort of giving a good sort of a performance. One thing that I also try to see very closely is that even in deep learning we will see that during the discharge we were having a bit of fluctuation during the machine learning model. Even if you look into the deep learning model, you will see that same thing reflect here. Just look at the charging pulse and the discharging pulse. You still see a bit of fluctuation which is there, right? Look at the charging curve. I believe with respect to charging, it is still very much accurately able to capture the fluctuation, but if you look at the discharging part, you still have this sort of a relation. How can you improve this further? Machine learning, we have had this at a much larger scale. Deep learning, we still have this. That discharging pulse, if you see, you can see the difference, clear difference, right? The fluctuation is more. But if you look at the charging, the fluctuation is sort of less. So this comes from the data itself. Because the data has that, we see the same in the predictions also. How can we improve this?
Either by modifying, filtering input data or adding some more features to the data.
So deep learning, we cannot add any more features. Deep learning itself, the way deep learning is there, deep learning by itself automatically takes out features. So deep learning, we cannot add any features separately, how we can do in machine learning. So deep learning, the way we can improve this, either by taking the input data that we have, that same data we might need to do some sort of a smoothing or averaging. That way we can make it slightly smooth, or we have to see how we can reduce the sensor error. So whatever sensor error that we have, if we can reduce that, then this will automatically have better sort of accuracy. So after this step, the main step is that I think there are 4 steps here given, just trying to see how to improve the data and all. So the last step typically is, I believe it's a very important step for most of us, is how we can take it to Simulink and integrate it into the Simulink model. So just opening up that part. So integrating in Simulink is actually very simple. Once you have a trained model, I can very quickly, just before that opens also, I can show you. So nowadays we have a number of libraries which are there that allow you to bring in any model here. So this is a Simulink interface. If you go to library browser and we are working with network, if you type, already I have typed it. So if you type network, you will find that there are a lot of blocks which are there that allow you to import network into Simulink. So not the 5G, 6G one, but if you go a bit down, so there are these libraries where you can import different sort of networks. So I'm not working with image classifier. If that was the case, I would use image. I can use predict blocks like this. So just drag that into Simulink environment. This predict block, I can go inside and I can import any network from MATLAB, any trained network. So this is where I will go and I will browse for the networks I have trained. So I think this is the SOC network compressed which I get here. So it has already identified that what type of network it is, and the input layer it has identified. Okay. So you can see the layer details also here, what sort of layers are there inside the model. And then I can do apply. Okay. And then the model is sort of imported. And this I can integrate it with any other model. Just like how I work with Simulink, I can take this and I can integrate it with any model. There has to be a sequence of input, and then this layer will give me the output here, which I can take anywhere. So this, as of now, this block will allow me to predict SOC, and this is what can be done here. So I believe, so now I can just, until this step it's clear, right? So I'll just take you then through the presentation to save a bit of time. So LSTM layer after we have created, then we can actually take and integrate. Alternatively, there is something also we can do. We can also, if needed, if there is a PyTorch model also, then also you can bring it into the MATLAB environment. It is also very common. What people do, people just import it. So in deep learning network designer, we have this option of importing it also. So if you have any open source network, you can import it from here. So this is a Python model. I am importing it in MATLAB and integrating it with a Simulink model. I can, only thing I have to do, I have to tell it what is the input layer size I have at my end. It will input it. You can see the entire network structure also. So this is a good thing that you can see the network and understand how the network is constrained. And then you can export it and you start using it in a Simulink model. And once you have imported it in Simulink, then code generation becomes very easy. So just to summarize what we have done so far, we have just created an AI model based on certain inputs and outputs. Okay. And there is some comparison here, just for our case. So Kalman filter was the conventional way of doing this, predicting SOC. Typically it handles very well. Okay. Some requirements are there, you need a lot of data to build an AI one, but typically for Kalman filter you just need a very accurate model. So this is the main difference when it comes to conventional method of modeling a state of charge estimator and an AI based method. AI you need lot of data. In the conventional approach you need a very accurate model. Okay. So in terms of history this is very well proven, and in terms of AI method it is actually emerging very rapidly. And there are plus and minus to everything. AI method, the main advantage is that if you change battery chemistry, very quickly you can train the model and it adapts very well. But data is actually needed. Okay. And third thing is that it doesn't need to be independent, you can combine both of them, Kalman and AI. But the benefit comes in integrating into an existing SOC and deploying it, because the memory footprint of this sort of models is less compared to a Kalman filter model. You need lesser size to deploy something like this. So we saw already there are libraries that allow us to integrate. So I have just one quick example to show you how to integrate in Simulink. I think this also we have seen. Specifically these blocks are there that allow us to integrate. You will have the selected AI model, you will have to give it certain input. This is something that we have seen. So maybe I'll just take you to the next steps, and once you've done something like this, then you can actually take the model and generate code for any given hardware also. So the models that we have built, it's code generation ready. Directly you can generate code for different sort of hardware. So this is just a snapshot of that. So you can do all of this processor in loop testing on different sort of processors. So processor in loop means that you generate code in your laptop only. It will generate C code out of the model, and you can connect a hardware. So you can take a ARM Cortex processor like an NXP board, connect it with your laptop, and the BMS algorithm will run on this ARM Cortex processor. Okay, and then it will communicate with your plant model, and you should be able to see the performance. So this is something that you can eventually try out. So once you have the model integrated, directly you can generate code for a specific hardware. For any given target, it will take the algorithm. No matter whether you have brought it from Python or trained it here, you will be able to generate code and compare the performance. Okay, so I'm not going to the details of this because I think this is something that might be tried on if you have hardware, so this should be possible. And any use cases, so we have one use case, maybe if you want to take a look at this. KPIT is an automotive company, they actually did it. So what they are doing as of now, they are going for hybrid approaches. So not just a conventional algorithm, they are taking AI-based approaches, combining it, and then they are trying to predict the state of charge and state of health of batteries. And not just this, like multiple companies are doing that for different applications. Like there are companies doing it for batteries, but there are automotive companies doing it for different systems, and companies like Coca-Cola also. So for measuring the amount of pressure, the amount of fluid coming out of a particular dispenser machine, they are actually having virtual sensors, not a real sensor. So maybe I will just stop here. I had one more example, but a similar sort of a thing on predicting the remaining useful life of a battery. But if you are interested, you can sort of take a look at the example later. I will just post the link. So it's more on the predictive learning aspect, like you can predict the remaining useful life of a battery. Same machine learning workflow, and then you can integrate it also. So this is the example: machine learning, lithium-ion battery capacity estimation. So feel free to explore this at your end and let me know if you have any questions. Apart from that, what I just want to quickly show is that for batteries and all, we are having on-ramps to get students started, and now we have some new ones also specifically in the area of advanced battery algorithms, state of charge estimations and all. So could be something that students and all can try out at their end. And we do have a curriculum specifically focusing on the entire EV modeling, where battery modeling and management is one aspect of it. Yes. And hardware support is already there. We were discussing with sir that if in your lab you have different sort of hardware. I heard there is STM32, you have TI boards. So from our side we also support these boards. So if you have any interest around that, we can plan some interactions in future, just for the hardware deployment aspect. Plus, students can take up challenges. So there are certain problem statements which we already list. So MathWorks has some projects which any student can take up. If they complete it, they will get a certificate from the MathWorks, the international team which is there. So actively, we monitor the submissions here. Very easy to participate. They just need to fill up a form and they should be able to participate. And problems are given according to different sort of research streams. Anybody can take up. If they complete and submit the file, MathWorks will issue a certificate from the international office, which has a lot of value.
You know, I already circulated to our faculty members. Please insist our students to participate.
Plus, it's mentored also. So, let's say the student gets stuck at any particular time. So, there is a dedicated discussion forum. And industries are partnering with us also on this. So this particular problem statement, the industry partner is STM. So they have actually proposed the problem statement. So academicians always say that can students take up industry relevant problems? So this is something that will address this exact requirement, and you can see there are detailed. There is a very good place for them to get started with. It's not like we just give you the problem statement. We tell that how they can get started. What is the first step? What will be the second step? So here if you see, it's an AI related example with predictive maintenance toolbox. Real-time monitoring, there is STM hardware related. I'm not sure if this is the same board. So you
Not
can
same, but different board.
It's a different board. I think. Yeah. So sir, the board sir has shown, I think that was a very good board because it had AI capabilities also. So these sort of projects they can do, and there is a dedicated discussion forum. If anybody has any questions, we should be able to reply to them and support either from here. If it is not addressed from here, then from Mathros office we will reach out to them and try to address it. So it's very actively supported. You can see that.
So this project, as we discussed in our FDP, which we haven't seen, so evaluation analysis will be needed. That's our feature. Same project you can guide the students. Only the board is different, the accelerometer is different. That's it, nothing else. So whatever we have done here, the same thing is here. You can ask the students, maybe you can mentor them. You can ask the students to submit. Because we have done it by FDP. I told you one of the sessions I was taken, I have taken. So I use some MPU 650 sensor. And here they just mentioned some dedicated sensors. So only those sensors they can take it.
So it's not like so what I say, it's not like a very constrained sort of a thing. There is flexibility. You can use different sensors. You can improve what the project accomplishes, what the student is about to accomplish. So it's not like a hard end. They have flexibility, and once they submit, they will be getting a certificate. Okay. So please just encourage students to take this up, and yeah. So, thanks a lot for attending this very interactive. Let me know if there are any questions or there is anything.
If we have any queries, we can interact with them.
Or please feel free to reach out to me. So,
See, those who are handling particular courses like MATLAB for control system, MATLAB for basic electrical engineering, renewable energy system, power electronics, labs, because we included MATLAB simulink everywhere, right? So we can discuss with him, you can send our curriculum to him. Okay, they may check and they will give some kind of suggestions how and what we can do with it, even the energy storage systems. Okay, can share the curriculum with them and they will come up with some more extra suggestions so that we can take it, and even they are ready to take some kind of lectures also from their side. Maybe as a part of your EAT you can arrange some kind of a session also. I discussed with him morning, so I requested the faculty please discuss with him.
so those are like very important things that sir emphasized. So we have support for curriculum and labs. So if you are planning to use MATLAB either in teaching or in labs, you can just connect with us, send us the curriculum outline, we can work with you to see how we can support you on that.
Thank you so much, sir, for your insightful session, and you have provided various, various valuable insights in the AI application for battery-based energy storage system. May I kindly request Dr. Prem Kumar to hand over the memento and LOA, this token of appreciation.
Post message. So thank you so much. Thank you for the session. So actually I will have a long association with you, so I discuss the meeting. So thank you for the session. You take one group photo.
Sure, sure.
No. Call everyone. Please. Yes. Not a feature. No problem. You will come.
We cover everyone.
मैम
Back side.
सिक्योरिटी
Gap. Thank you. So all of you please be here. So we have a presentation.
Sure, I will share it with you. Okay, even I will share the curriculum also.
That will be
We also have already something made, but it's better to do the review and then give some more inputs on that. Even this AI board also.
We'll take care of something.
One thing I will take. Please check the.
Definitely.
I am on board now.